So I'm going to look at this carbon right here first, okay? And the way that it helps me to think through this is I like thinking about how many electron domains we have around that carbon. So how many electron domains do you see around that carbon I boxed in blue? I see 4 electron domains. And those 4 electron domains are 4 bonds in this case. 1, 2, 3, 4. So are we all comfortable with that language? All right. So if it's got 4 electron domains, what shape do we consider that molecule? Yeah, so around that carbon atom, it's tetrahedral. I'm not saying the entire molecule is, but around that specific carbon atom, we'd say the shape is tetrahedral. Now, that's the electron domain geometry and the electron domain shape because I have no lone pairs of electrons. So do you remember the distinction between that? That I can have a tetrahedral kind of geometry, but then my shape would be like trigonal pyramid or something if I have a lone pair. In this case, we don't have to worry about it. So my electron domain geometry and shape are both tetrahedral. So if you are tetrahedral shape, what are your approximate bond angles? And this is something you just kind of have to memorize. Yeah, they're going to be around 109, 109.5 degree bond angles, okay? Okay, so the thing that's really important about that is that sometimes when we draw these molecules, we don't draw them to accurately reflect that. Okay, so if you look at the picture we drew where we had up and down bonds here and up and down bonds here, well, if you took the angle right there, that's a 90-degree angle the way I drew it, right? Just because we draw it on paper, draw the Lewis structure with a 90-degree bond angle, doesn't mean that that's what it looks like in real life. So what we're trying to get you to understand is that on paper it looks like 90, but it's really about 109 because it's that tetrahedral shape. So those are the appropriate bond angles around that carbon there. And if I know that it's got 4 electron domains, what does the hybridization have to be? SP, how many? Yeah, so this has to be sp3 hybridized because we know that if it's got 4 domains, and we know we've got 4 orbitals to use, we've got 1 s and we've got 3 p orbitals. Well, if it's got 4 domains, it's using all of them, 1 s and 3 p's. That's why it's sp3 hybridized. Questions about that first carbon? All right, let's do the one next to it. Let's do the carbon in red. Same idea. How many electron domains would you say are around the red carbon atom? This time only 3, because I count the double bond as a single electron domain because it's only going to one other atom. Any questions about why I'm only counting the double bond once? Okay, so if it's got 3 electron domains and I can see that they're all bonding, what would we call the geometry, in this case also the shape, around that carbon atom with 3 electron domains? Trigonal planar, yep. Okay, so if it's trigonal planar, we should know the bond angles associated with being trigonal planar. What are the bond angles associated with being trigonal planar? Yeah, so about 120 degree bond angles. And the reason I'm saying about is because you probably remember reading from the textbook that the lone pairs on surrounding atoms and on the atom itself can kind of push the bond angle so that they're not precisely where we think they're supposed to be, and that's why I'm just giving you a rough estimate that it's around 120. Okay, so we've got the domains, we've got the shape, we've got the bond angles. Next thing we want to talk about is the hybridization. So remember that I've got 4 orbitals to work with. I've got 1s and 3 p orbitals that I can work with, and I can mix those together to form hybrid orbitals. If I need to have 4 electron domains, I mixed 4 of them together. If I only need 3 electron domains, I only have to mix 3 of them together. So what am I going to mix together to make something with 3 electron domains? 1s and how many p's? I'm only going to put 2 p's together. So that's going to be sp2 hybridized. Any questions about why I know it's only sp2? Because it's only got 3 domains around it, so I only needed to mix together 3 atomic orbitals to get those 3 hybrid orbitals. So what's happening to that other p that I'm not using? What do we call that other p that's not part of this hybridization process? Do you remember that language? One unhybridized p orbital. Okay, so basically the opposite of being hybridized would be unhybridized. So if I've got one unhybridized p orbital, what do I use those unhybridized p orbitals to make? What can I do with them? I can make a double bond because I know that a double bond contains what kind of bonds? How many sigma, how many pi? Yeah, so specifically that unhybridized p orbital is being used to make the pi bond, so p orbital, pi bond. So I can tell that it's okay for that carbon to have that double bond because I know that it's got one unhybridized p orbital that it's using to make that pi bond. Okay? Any questions about that language? So if I went through and counted on this entire molecule, how many pi bonds are on this entire molecule? Just the one. Okay? And then everything else is a sigma bond. And how many sigma bonds did you find on this molecule? You should have found 9 sigma bonds. Remember that this double bond here, what is that double bond made up of? 1 sigma and 1 pi. So that's how we count the double bonds. What if it was a triple bond? What would it be made out of? 1 sigma, 2 pi bonds. Right, so everything always has 1 sigma in the center. Remember, sigma is that direct overlap. And then if I put 1 pi bond, that's a double bond. If I put 2 pi bonds, that's a triple bond. But in this case, 1 sigma, 1 pi in there, total of 9 sigmas in the entire molecule, 1 pi in the entire molecule. Questions? Okay, I know I didn't do the oxygens or the nitrogens, but it's the same general idea. Any questions about how to do those? All right. For the sake of time, I'm going to let you guys go on the quiz and let